Hello, welcome to this next video. In this video, I'm actually going to be motivating the transition to quantum mechanics. But before I get there, I want to talk about discreteness in nature and the wave-particle duality. And so here on the left, actually, you see what is known as a hydrogen spectrum, which you can obtain actually by experimentally measuring the photons or the light that is emitted by an excited hydrogen atom. And so if we isolate a hydrogen atom, so we have a proton in the center and an electron orbiting it, and we somehow excite this. We can excite this thermally, for example, or we can excite it by exposing it to some high frequency light. The actual atom and its electron will jump to a higher energy state and relax back down, and it will do so over and over again. It will just keep on emitting, absorbing, and the actual spectrum, the so-called spectrum that is emitted, takes on this form. And this indicates that there's some discreteness in the energy levels of the hydrogen atom. That's what this indicates. And so this experimentally, this has been measured, back in the 19th century. And later down the line, the actual energy values using quantum mechanics, there was actually the Bohr model that was able to model this, but just putting that aside, quantum mechanically, we were able to really convince ourselves that there are these discrete values within the hydrogen atom, and the actual energy states take on this form here. So what that means, and this is just to give you one example of this, is that if I take the second energy state and I say subtract the third energy state, what I actually end up with, and so here, if I have like the first energy states of the hydrogen atom, so this is the lowest, E0, I can call this E0. Then I can have the second energy state of the hydrogen atom, I can call that E1, and E2. And actually, just to be a bit, just to be consistent here, I'm going to call this E1, the ground energy state. I'm going to call this E2 and E3. If I calculate this particular transition here, from this energy down to here, right, this energy level, I get a value that is actually equal to 1.89. So I have 1.89 electron volts. This is the units of electron volts. We spoke about that in the previous module of lectures, the previous set of background physics lectures. And so if I convert this into light, right, and I know how to convert this into light, I actually deduce a wavelength, or sorry, did I say deduce into light? I meant wavelength. And so if I actually take this electron volt and I convert it to wavelength, I have a value that is equal to about 656 nanometers. And so the reason I'm doing this is because this wavelength here corresponds to this energy level that you see right here. And so the transition from the third energy state to the second energy state of the hydrogen atom emits this line here. And so that's just one example. I can move on to the photoelectric effect. And the photoelectric effect is really interesting, and it really kind of manifests this sort of wave-particle duality pretty well. And what it says is this. It says if I take a red light, or actually not red light specifically, but any light that, some light, not any light, but some light that has a sufficiently low energy level. So the photon energy of the light here is really low. So let's say it's very low. I can actually blast a sample of, say, metal. Really, it could be anything, but let's say it's metal, for example. I can really blast this with a very, very high frequency photons. So I'm going to draw this to kind of like draw the beam. This is a so-called beam here. And this can be very powerful. And If I do that, in principle at least, I will not emit any electrons from the sample, which is interesting because, I have, even the piece of metal is consists of, outer electrons, right? Looks something like this, just as an example. And you would think that if I emit light that is absorbed by this electron, eventually, if it gets bright enough, so to speak, or intense enough, I'm going to have an emission of an electron. But it actually does not happen, right? And this has to do with the actual discrete energy of individual photons. And so this goes back to discreteness, and it also goes back to this wave-particle duality, because although classically you may be able to deduce some relationship between the amount of energy that is absorbed by this metal and the electrons that are emitted, classically there is no way you can determine why the wavelength of the actual light is important here. Because if I take this here, if I take a very low frequency or very low power, not frequency, a very low power UV laser, even so low that I'm getting just one photon at a time, I am indeed going to have some fair amount of electrons emitted from my piece. And so, strictly speaking, I'm assuming here that this photon energy is just very high. It's not all of these, the strict values really just depend on the material or my target, and the material and the target actually sets the defined value that I need to set this laser at. But just to be brief, we're going to presume that the electron energy or the photon energy is very high, and if it is, even very low intensities, even one photon at a time, can emit electrons out of the sample, right? So this really ties into discreteness and wave-particle duality, because for some reason the wavelength of light is key to the emission of photons. So moving on to this next phenomenon, which is the black body spectrum. Why is this important? Well, just to be really brief here, we have like a light bulb. I'm going to take this light bulb just as an example. And we know that if we heat up a filament, say a tungsten filament to a high enough temperature, we're going to get a fair amount of emission of light. We're going to get a fair amount of emission of light. And we can actually, measure, if we have some sort of apparatus, some spectrometer, measure the number of photons that are coming out of this light bulb for every given frequency. And we can actually do this. And so if we have, like, say, the intensity or the number of photons coming out per unit area per second, and the wavelength, we're going to have a spectrum that looks, just roughly speaking, something like this, right? And so, I'm going to have a bunch of photons coming out, and I can measure this with some apparatus, right? I can measure this with some apparatus, and then calculate sort of what energy this photon has, and then what energy this photon has, and then calculate the number of photons coming at each individual energy or wavelength, and create this spectrum out of it, right? And one of the things that I'm going to discover is that the only thing that this spectrum is dependent on is temperature, which is why you have these values here. It's the reason why you have these values in this plot. I didn't mean to do that. There you go. The values of these plots. And so that's quite an interesting phenomenon, believe it or not. And it turns out that the physicists at the time really wanted to model this curve here. They wanted to model this curve, and they were not able to do it unless they presumed one thing and one thing only. If they presumed that light was discrete, or it came in discrete forms, then in this case, Max Planck, the curve that takes on this form was physically able to be deduced or calculated. And so beforehand, presuming light is not discrete or continuous, there was another spectrum that just completely failed, and this is kind of known as the Rayleigh, you can look this up, the Rayleigh-Jean approximation. This is sort of like the classical interpretation. And for low wavelengths, this really failed. So for low wavelengths, this approximation really failed. And so assuming continuity in the intensity of light was not the right approach. The right approach was to presume that light came in discrete packets of energy. And that, when presumed, allows one to calculate this spectrum. And it also allowed for another very important constant to be calculated. And that is known as Planck's constant. And so if you take the energy of a photon and you take its frequency, which can be determined through other classical means that was well developed back in the 19th century, you realize that they're off by a factor of h, which is defined to be Planck's constant. So Planck's constant, or Planck's constant, I believe it's pronounced as Planck, is equal to 6.626 times 10 to the minus 34. And to be brief, one of the things that Planck's constant explains or sort of models is the resolution of the discreteness of light, right? And so Planck's constant comes up over and over and over again, and it's just sort of like the resolution of the discreteness. And so when someone asks how discrete is light really, and that can be a complicated question, but however you answer it, you know you're going to be talking about Planck's constant here, right? So like the smallest amount of energy, in other words, that I can add on to a beam of light is going to be a factor of Planck's constant. It can't be just a fraction of it. That's impossible. So all of this said, this brings me to de Broglie's hypothesis. So what is de Broglie's hypothesis? So before just defining that, we know that light comes in, or not comes in, but can be interpreted as waves and particles, right? And so waves was like the traditional interpretation, clearly, for hundreds of years. And then came the idea of a photon, and it was well accepted that, yes, okay, there are some particle-like features of light. But what about particles with mass, like an electron or a proton? What if this can also be calculated or interpreted as waves? Because, it's trivial to regard them as particles, and this is how, ontologically, this is how we've always referred to them as, like in classical mechanics, for example. But waves, this is confusing. And so de Broglie said, well, if there are some wave-like features in particles with mass, then the wavelength of these particles with mass will be equal to the Planck's constant divided by the momentum of that particle. So this is the very important hypothesis that really led to the production of quantum mechanics, because fundamentally, because we have light and waves physically modeled using electromagnetism or Maxwell's equations, what about particles with mass? What do we use to sort of link particles with mass with waves? And the answer to that lies in Schrödinger's equation, which will be the subject of the rest of this course. And so de Broglie's proposed that matter can also be regarded as waves. And so if that is true, some wave equation should exist for matter. And that equation is Schrödinger's equation. And so we're going to get into that in the next lecture, and we're going to learn how to apply it in a variety of different cases. And so I hope you enjoy it, and I hope it's fruitful, and I'm looking forward to it. So I'll see you guys in the next video.